So, chirality. First of all, an object can be either superimposable or not superimposable on its mirror image. For example, a square is superimposable on its mirror image, however a left hand is not. If an object is not superimposable on its mirror image, then that object is deemed chiral. This is the same for molecules. Molecules can be either chiral or non-chiral. For example, the molecule methane is non-chiral because it has 4 of the same groups attached to it. However, a carbon with 4 different groups attached to it is called chiral, and the carbon in the middle of the molecule is called a chiral center by IUPAC. So, a compound has an enantiomer if the compound is chiral. 2 compounds that are mirror images of each other are called a pair of enantiomers, but only if that compound is chiral. This is much like a pair of gloves, where the left hand and the right hand are mirror images of each other. Compounds can only have 1 enantiomer because a compound obviously can only have 1 mirror image. Now, on the topic of drawing enantiomers, you can place a mirror behind, beside, or below the molecule, and imagine the molecule just reflecting on that mirror, and you will draw that reflection. But you have to consider bonds going into and out of the page, and that will be reversed if you decide to picture putting a mirror behind a structure. Now, obviously, enantiomers will have identical physical properties. Since they're all made up of the same atoms, all the intermolecular interactions are identical in a pair of enantiomers. A famous example of this is the molecule methamphetamine. D-methamphetamine is an illegal drug, while L-methamphetamine is a nasal decongestant, but both share the exact same boiling point of 212 degrees Celsius. Next up is the Cahningold Prelog system. This is a system for nomenclature to identify each enantiomer individually. There are 3 main steps that you have to do. Firstly, you have to assign priorities to each of the 4 groups attached to the chiral center. The highest atomic number will be priority 1, the highest priority, and the lowest atomic number will be priority 4, the lowest priority. If 2 atoms attached to the chiral center turn out to be the same, then you'll check which atoms are attached to these 2 atoms and write them in decreasing atomic number for each. For example, there will be CHH for a methyl group and NHH for an amine group. Now, you will compare adjacent atomic numbers in decreasing order. Whichever has the highest atomic number will have the higher priority. The amine, in this example, will have the higher priority. If it's a tie, then you just move on to the next closest atom and then do the same thing again. Now, once you're done assigning the priorities, you will now rotate the molecule so that the lowest priority group, priority 4, is directed into the page using the dashed lines. To rotate a molecule, you will switch the lowest priority group with the group that is on the dashed line and then switch the other 2 groups. Then, you will see if the 1, 2, 3 priority sequence is counterclockwise or clockwise in the molecule. If it's counterclockwise, then the structure is deemed S from sinister, and if it is clockwise, then the structure is deemed R from rectus to describe the configuration. Now, you can name the molecule based on this system. When naming a chiral compound, you must specify the R and S configuration in parentheses for the compound name. An example is R2-pentanol or S2-pentanol. If multiple chiral centers exist, each configuration must have a number to indicate the position on the chain. For example, this is 2R, 3S, 3-methyl, 2-pentanol. Now, time to move on to the final topic, optical activity. Now, a bit of a review. Plain polarized light is light that has passed through a polarizer, so only photons of a particular polarization can pass through. Now, compounds that are able to rotate the plane of polarized light are called optically active, while those who can't are known to be optically inactive. Enantiomers will rotate the plane the same amount of degrees, but in opposite directions, since it is one of 2 molecules that are mirror images of each other. Now, to talk about optical activity, we need to talk about specific rotation. When an optically active compound is placed in a polarimeter, a device used to measure the polarization of light, its observed rotation, which is symbolized by the Greek letter alpha, change in orientation of the polarized light and is unitless, is dependent on the number of molecules the light encounters, and is directly proportional to that. So that means if the concentration is doubled, the observed rotation is also doubled. Similarly, if the path length is doubled, then the observed rotation is also doubled. Now, specific rotation is an observed rotation under standard conditions. Equation for specific rotation, as you can see on the screen, where alpha in brackets is the specific rotation, alpha is the observed rotation, C is the concentration in grams per milliliter, and L is the path length in decimeters. It all comes together to the equation specific rotation is observed rotation over the value of concentration times path length. Specific rotation is also dependent on temperature and wavelength. The relationship between these factors and specific rotation is not linear, therefore they cannot be used in the equation. Compounds that exhibit positive or clockwise rotation are dextro-rotatory, symbolized by D, while compounds that exhibit negative or counterclockwise rotation are called levo-rotatory, symbolized by L. Now, whether a compound rotates light in a positive or negative direction can only be determined through experiment and not from the Cahningold Prelog system. Now on to the topic of racemic mixtures. Racemic mixtures are mixtures of a pair of enantiomers of D and L, much like dextromethamphetamine and levomethamphetamine. On the contrary, an optically pure mixture only has one type of enantiomer in it. For racemic mixtures, there is a specific value called an enantiometric excess. This is a difference in percentage of the percentage composition of enantiomers. For example, if one enantiomer makes up 60% of a solution and another makes up 40%, then the enantiometric excess in this case is 20%. Thank you for listening to this video. Please come again.